We were looking at the energy equation, so here we rewrite this again, where we now look at term by term. So this is essentially the inertial term of enthalpy flux, right? And so the enthalpy is now of the mixture, and so H is now written as sigma yk hk, where hk is now the specific enthalpy of species K, which can in turn be written as the standard heat of formation of that species plus the sensible enthalpy. Okay, this is a specific sensible enthalpy of species K, and temperature is an unknown that is sitting on top of this integral here as a upper bound. Of course, if you want to rewrite this equation in terms of internal energy instead of enthalpy, you could derive this from noting that you can write this as Ek plus Pk divided by rho k for this Hk, and proceed from there. Now let's look at the second term. This is the first term on the right hand side here, which is the q vector, which is the heat flux vector. So the heat flux vector is essentially coming from from the sides of a particular point in this in the domain, and the first contributor is the conductive heat flux, which is given by the Fourier law. So we are assuming a fluid that would satisfy the Fourier heat conduction. K is the thermal conductivity of the mixture. Okay, so when you now have a mixture of lot of species, we have to ask what is this K. So similar to the question that we asked about mu, we have a similar question on K as well. This is basically transport properties of mixtures, which is something that we will have to go back to kinetic theory or molecular level to deduce. We will not do this now. I will just put out an expression in a website. This is coming from the fact that you have a diffusive component of enthalpy flux in addition to the mixture averaged convection, right? So this takes care of the mixture average. Okay, so this will actually convect the enthalpy of the mixture at the mixture average velocity, but in addition to that, the species is also taking with it enthalpy of itself at the diffusion velocity. This is what this represents, which was sort of left out previously. So you have a negative sign here that will take care of the fact that if you now take it to the left hand side, that would add up on the actual enthalpy that is taken by the species. This is a term that is the counterpart of the Soret effect that we saw in multi-component diffusion. This is called the Dufour effect. As you can see, you have the thermal diffusion coefficient dTi divided by dij showing up, where dij is the familiar binary diffusion coefficient, and we had noticed the thermal diffusion coefficient earlier as well in the Soret effect. There we were looking at a temperature gradient contributing to a concentration gradient. Here it is the molecular diffusion velocities disparity. The disparity between the molecular diffusion velocities is what is actually contributing to a heat flux. Okay, so it's the opposite of what the Soret effect describes, but by a similar process or at the molecular level again. QR is a general term that's been written out to take into account radiative heat flux, alright, but you should now be able to expand this, taking into account things like shape factors and emissivities versus absorptivities and all those things for the surfaces as well as gases that are involved in a volumetric or surface manner and so on, with a t to the power 4 dependence, putting the Stefan's law and all those things. So if you want to bring in radiation into account, there we are. Q dot is an external heat release rate. This is the volumetric heat release rate. This is actually having this units like watts per meter squared. So you're looking at actually a heat flux over here, but this is more like a watts per meter cubed, because we are looking at volumetric heat release that is within the domain. So this is typically coming from things like if you now have a very complicated geometry of something like electrical wire, or let's say nuclear rods or something of that sort that is giving rise to heat that is outside of the fluid, but you want to now keep that within your domain because it is too complicated for you to negotiate the fluid within these parts, but you want to just kind of say on a spatial distribution basis the per unit volume heat release rate would be so and so, if you want to just plug that in. This is not the chemical heat release rate, okay. The chemistry is part of the fluid mechanics, it is not external, this is external, okay. The chemistry is part of the fluid mechanics sitting here in the delta HF naught K, that is the standard heat of formation of species K. If you now take that into account and then add that up weighted by the individual mass fractions of species each species, then you now get the summation for the standard heats of formation that tells you how much heat is actually released by taking in the heats of formation of the reactants and releasing the heats of formation of the products, alright. So that is already taken into account in the H, it is embedded there, it is not external. This is coming from the fact that, recall, this equation is a thermal energy equation. You could write out the total energy equation by writing an equation for these for conserving the stagnation enthalpy, right. The stagnation enthalpy would have the static enthalpy plus the velocity squared by 2, right. And how did you get this? You now take a dot product of the momentum equation with the flow velocity, which is flow means mixture mass averaged velocity of the mixture, then you get what is called as a mechanical energy equation. You subtract the mechanical energy equation from the total energy equation to get the thermal energy equation. While you did that, in that equation you had a body force per unit mass term showing up, alright, and the body force got dotted with the mixture averaged velocity, alright, but each species is actually getting acted upon by the body by a body force that could be unique to that particular species in the first place, and secondly the work done by the body force is on the species velocity. A species is trying to move at a particular velocity, small vk vector, okay, and then you now have a body force that is acting on it and trying to do a work on this. So the work actually should be a dot product of the body force or acting on that species per unit mass, okay, that is essentially acceleration there, okay, times the species velocity. But we took a dot product of the mixture average velocity. So the species velocity is nothing but the mixture's average velocity plus the diffusion velocity, and we subtracted only one part of it, which is corresponding to the mixture average velocity, but there is still another part that is remaining, which is based on the diffusion velocity. That is the reason why we are getting this, okay. And then this term is a viscous dissipation, and we write out the viscous dissipation over here, which is again notice this is again using the tensor index, Cartesian tensor index notation over here, and we are applying the Einstein's summation rule, okay, or rule of summation over repeated indices. We are having two repeated indices here, I and j, both of them are repeating, alright. So tau ij is actually 9 terms, so it's a second order tensor, so it has actually 9 components, and dou vi by dou xj is going to be again a tensor, okay. So this is like a dot product of 2 tensors, alright, and so essentially what it means is that you are now having 9 products that are all getting added up together, alright. And so we run I in 3D. We run I going from 1 to 3 and j going from 1 to 3, and then we will add up all of that, okay. Now how did we get this? If you go back and look at your momentum equation, you had a dou by dou xj of tau ij, which gave you the ith component of of your shear force per unit volume, okay. So you had a spatial derivative of your shear stress, and we were dotting that with ui or vi, okay. So our work done by the shear stress should have been something like Vi dou by dou xj of tau ij. That is what we should have had. That is actually the work done in the mechanical energy equation, okay. Here we would have actually had a term that is more like dou by dou xj of tau ij dou by dou xi of tau ij Vi, okay. So here what you are doing is that is in the total energy equation. So the total energy equation, you now look for what is the full work that is done by the viscous stresses, and then in the mechanical energy equation you now have a term that is dotted by the shear force with the velocity, right, and then you subtract that. This is what you would get. You can actually show these things as an exercise, and we will post these as exercises for you to show, okay, while you are doing this course. And finally, of course, we now have this dp by dt term that is coming primarily on the right hand side because you are working with a enthalpy conservation. If you were to work with an internal energy conservation, you will now notice that you have a Ek plus Pk by rho k. You can now plug that in here. You now have H that is now summing over Yk Ek plus sigma Yk Pk by rho k, and then you can now identify this term on the right hand side if you are now trying to conserve internal energy instead of enthalpy. But effectively this is a term that is going to come up primarily because this is the pressure work term essentially, okay. There is pressure that is acting on a flow that is moving, and because the flow is moving, you now have a gradient in pressure that is acted upon by velocity. That's as if like you now have a pressure force that the flow is up against, and therefore you have a work that is done by that. And this is typically something that comes up for compressible flows. You don't have to worry about it in incompressible flows, alright. So this is the energy equation. Finally we have to close the set of equations that we have had with this expression for Wi, which is in turn containing your temperature and the concentrations, alright, because this Wi showed up on the right hand side of the species conservation equation, and that was kind of like an unknown until we tried to relate it to a set of previously agreed unknowns. The set of previously agreed unknowns was concentration. This is a mole fraction. Of course what we enumerated first was the mass fraction Yi, but the moment you actually use the multi-component diffusion equation, that equation was on grad xi, so we had to now start reckoning xi as our unknowns, and therefore we have to have a set of equations that relate xi and yi. That is readily available, that is an algebraic equation set. So you will now have to reckon xi's also as unknowns and show that and see that it shows up here in this expression, in addition to the temperature showing up at a couple of places, and this is the ugliest place where it shows up, okay. And I would like to remind you of this. This is the temperature sitting in the denominator of a ratio which is taken which is risen to an exponent with a negative sign, alright. So this is a highly there is a high degree of nonlinearity here. That simply means that as the temperature increases, this term will actually increase in a highly nonlinear fashion. That means it is not going to rise as rapidly for low temperatures, but it is going to go boom with a slight change in temperature beyond a point that depends on E, okay. Higher the E, greater this nonlinearity, or the greater the sensitivity of the reaction rate to, or the production rate in this case for of the ith species to temperature, okay. So higher the E, the greater the delay in temperature axis for this thing to go up but the moment it begins to go up it goes to very high values. Okay, so that is the nonlinearity that this brings in, which makes it very difficult for this set of equations to be solved. Already we are beginning to look at a fairly ugly set of equations in terms of just being partial differential equations that are nonlinear, not necessarily nonlinear primarily because of the convective term, but there are all other kinds of nonlinearities that we are also beginning to look at in terms of what the multi-component diffusion equation, even the Fick's law for part of it shows up for you, and then you see this nonlinearity here. This is actually a product, okay, this pi is actually a product of a lot of unknowns over here, all raised to coefficients that are not 1. Okay, anytime you have a power other than 1 you have a nonlinear term, and you now have products of those that is making it miserable, and on top of it you now have a very nonlinear term that is sitting there. So this is a horrendous problem as far as combustion is concerned. So with this we can actually complete the set of equations. So what all have we done so far in this full set of conservation equations? Well, of course I think I just missed one more equation of state. Equation of state which is P equal to rho or ut times sigma k equals 1 to n yk divided by wk. This is pretty much the way the mixture molecular weight is defined. Alright, the mixture molecular weight is primarily defined through what's called as Dalton's law of partial pressures. Right. How did you get the Dalton's law of partial pressures? We know from basic definition of density that you simply have to add up the densities of the individual species to get the mixture density. Alright, and then the Dalton's law of partial pressures is the one that says that if you want to get the pressure of the mixture, it is a addition, it's a summation of all the partial pressures. So that's essentially the way we can define the mixture molecular weight. Okay, or in other words we now say that the mixture will also have to obey the perfect gas law just as well as the individual species, and if that were to be the case, its molecular weight should be like this. Alright, or in other words you are saying 1 over the mixture molecular weight is equal to 1 over sigma k equals 1 to n yk divided by wk. That's how we are that's how we are doing this. So why did we need these equations, right? So what we have to look for is what are the unknowns, and then what are the corresponding, in some sense all these equations are linked to each other, they are all simultaneous set of equations, you can't solve any of them independent of the other. Okay, so you need the entire set, and still what we can think of is each of these equations is meant to be like an evolution equation for a one particular unknown. It's unfortunately that it also involves other unknowns for which we will go in search of other equations, which in turn will be evolution equations for some specific unknowns in our mind. Okay, so this is easy for us to actually try to tag equations and unknowns together. Okay, so that we can enumerate them together and make sure that we have the same number of unknowns as the number of equations ultimately. Okay, so the equations, the list of equations the list of equations and unknowns. One, the first thing that we have is overall continuity equation, right. Now this equation involves rho and Vi, where Vi is the ith component of the mixture, the mass averaged velocity of the mixture, This is not the species velocity, this is the or if you want to use a vector notation which is a little bit less confusing, we could simply say v vector. Okay. That means you now are looking at 3 components in 3D for you to have, but it's only one equation. It's a merciless equation. It just puts all the mass together regardless of which direction in which things are going, right? Therefore 3 components of velocity and density all together will have to be tackled in this equation. We would now reckon this as something that's an evolution equation for rho, so that's one unknown. Okay, we still have 3 more unknowns to account for, so we continue to go in search of equations. So if you're now looking for a vector as an unknown to be solved for, you now look for a vector equation. The momentum equation is a good equation for us. So 3 components of mixture momentum conservation, right. This involves this continues to involve rho, which has already been enumerated, not a problem. This involves the v vector, all right, that's good. So this things could have been nice if it just stopped here, but unfortunately it involves p, which means we will have to now go in search of one more equation at least for p, okay, and then we will find that that involves t, and then we will find that involves something else, and so on, right. So that is how our lives are, okay. We go in search of more and more goals, and then they get you into other problems and so on. So that is what that's how combustion is so lively. Here what we would like to keep is this equation is meant as an evolution equation for velocity, the mixture velocity. So this is actually three unknowns, right. So all I am asking you to do here is match the number on the left corner to the right corner. We should try to look for that. So long as we keep doing this, we should hope that finally we will have the same number of unknowns as the number of equations, okay. So we still have one more unknown that we have to write an equation for, and let us suppose that we can pick the energy equation. The energy equation does contain p, although it's not really an evolution equation for p, okay. We will now see that it involves other unknowns. So one energy equation. Now this involves a lot of new unknowns, right. So it involves rho, which has already been, it's not a new unknown, it's an old unknown. It involves v vector, all right, that was sitting in the capital D by dt, okay. In fact, the way we can actually find out unknowns is to do it like the way you would do if you are a computer. So you just scan, it's like rho, is it an unknown? Yes, it is unknown. D, that is not an unknown. H, is it an unknown? H is equal to yk, that's unknown, 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 k times, okay, so n times, and then you keep doing this, and then you will find the t's, and so you can just very blindly, you don't have to be a genius, okay. So it's not a very difficult thing to do at all. Just have to be very patient, plodding through equations term by term, letter by letter, okay, and then you can find that v shows up there, and yeah, we did that, right. So we now go from here, we go there. Oh, k is an unknown, k unfortunate. Now for the first time that's n unknowns for you, okay. That's capital N unknowns, and capital N could be 40, 50, 100, okay. So that's one of the nightmares that is now beginning to show up. But anyway, we are now looking at only one equation, okay, which is supposed to be like a template equation for an evolution of something. As we now go, hey, hk, this is fine, that's given t sitting there is an unknown, and that's what we would now like to tag this equation as an evolution equation for. So we have T enumerated as an unknown already now, and then what else is going on? So you now have Q has this K that's supposed to be given. Well, strictly speaking it depends on the mixed fraction, so it's an unknown, but we now have to write equations for that relationship between the K and the mixed fraction. Okay, so you can always look at a lot of things as unknowns and then provide equations for each of those. Okay, but let's not do that at this time. T is counted, Hk contains T that is counted, Yk is counted, Vk. Okay, that's a pain. Why is it a pain? It's n diffusion velocity vectors. That means there is actually 3n unknowns in 3D for 3 components of each and every species diffusion velocity vector, right. So that's a lot of unknowns just proliferating by the minute with the energy equation. Looks like a big villain here. So we had this is okay, so we have already counted all these things, we are doing fine. And then we go back here, Fk is supposed to be known, P is already counted, phi involves essentially the mixture average velocity that's been counted. Good. Okay, so what have we come across over here? It is we will now look at this as a evolution equation for T, which is one unknown, but we are grossly underestimating the problem here because we have now to reckon 3 unknowns here and 3 n unknowns here and 1 n unknowns here, right. So we are short of 4 n equations. Okay, the good news is anytime you are short of a equation for a vector, you look for a vector equation, because the vector equation will give you 3 components by itself. Alright, yes. Pressure is also there, yes. P is also there. Fortunately for us that's been counted. Okay, so that's not an extra unknown anymore, thank you. So we now are now hunting for 4n equations. Okay, so what is the first equation that we can think about that is like a set of n equations? That's the species conservation equations, right. So the species conservation equations are n species conservation equations. N species conservation equations. And what do the species conservation equations contain? They contain your yk, right. So we had a dou yk by dou t as the first term, unsteady term. Then we had a convective term which involved the mass average velocity of the mixture v vector, small v vector. Then we had the diffusion velocities of species. So right, we had this, right, and then we had let's say wk. You either write wk here and then count this n equations separately, or you now say, well, I can plug this expression on the right hand side of that and note that it has these x and t and so on, so I don't have to write separately this expression. It's just one term, one huge term that can be plugged on the right hand side of that equation without having to count it separately. So let us suppose that this is what we have. Now I would like to look at this equation as an evolution equation for yk, that is n unknowns. I want to basically say this n corresponds to an n there, so just for the purpose of tallying, okay, every step of the way. Okay, what have we not still done? We don't know what is this. okay. Is that all? Not quite. If you were to plug this, if you are to plug this in, you now have a xk or an xj. That's not the same as yk, unless all the molecular weights are assumed to be the same, which is not necessarily the case in general, right. So we also have to now reckon the mole fractions of individual species as unknowns, alright. Okay, so we are now still stuck with chasing 4n unknowns, okay. Fortunately for us, when we are now looking for a evolution equation for this is a vector, and we can now look for a vector equation. So 3n multi-component diffusion equations, right, in 3D of course, right. So this involves yk, alright, xk, alright, capital Vk, alright, and then we also had p, t, things, all those things that have been counted so far, right. So what it basically does for you, unless I am missing something more, just point out if you have the equation right in front of you, you can go back to see if anything more is involved in here. A small fk vector is supposed to be given, it's not considered an unknown, and similarly other parameters like dij and dti and so on are considered to be given, okay. So here I would like to look at this equation as a evolution equation for, it's not really an evolution, it's not evolving things, but it's basically a constitutive relationship for capital Vk vector that gives you 3n unknowns, 3n unknowns. So you have a 3n here and a 3n there, that is okay. But what are we still missing? We still have to count xk, right, as n unknowns. Therefore there must be one set of n equations, n relationships between yk and xk involving all the molecular weights, okay. Did we close the set? Maybe not. Just go back. We have taken care of rho, we have taken care of v, we have taken care of t. We still have to worry about p. We started out with thinking that we will go through the energy equation in search of p, but we tagged it to t. So we have one equation of state, this involves p rho t, and go back here, it involves yk. Now everything in this is now counted, okay. So this is this I would like to look at as an equation for p. So one unknown, So how many, what's the full set of equations that we have to solve? How many unknowns are we having? Let's look at what we don't know first. We don't know a lot of things, right. So the easiest thing is to look at the unknowns. So you now say we have a 1 plus 3 4 plus 1 5 plus n, 5 plus n okay, 5 plus n plus 3n, that is 5 plus 4n. So this is now for xk, this is n unknowns. So we were counting 5 plus 5 plus n over here, and then now you say 5 plus 4n, okay, and then this is 5 plus 5n, this is 6 plus 5n. So we are essentially looking at a total set of 5n plus 6 unknowns, and we have 5n plus 6 equations to solve for. Okay, this is a question that was asked for me in my PhD qualifying exam. Okay, what is the total number of equations and unknowns in combustion? Okay, and list them. That means you have to list both the equations and the unknowns. Okay, so you just have to mug this up, 5n plus 6. That's like a magic answer. And then start scratching it, and so on. Start counting, thinking. Okay, but this is actually a decent way to think about this. Like each and every equation is supposed to do the job of solving for you an unknown. Okay, but it involves other unknowns that we will now go in search of for other equations. Okay, and then we have to now close the set. This is essentially the idea over here. 5n plus 6, what does that mean? Even if you took a modest number for n as like 20, you are in trouble. We are now looking at 106 equations and unknowns that we need to solve for, and these are ugly looking equations. Okay, if you were to take a more realistic situation of 40 species, okay, you're now looking at 206 equations. You see the problem, right? So there are people who do these things. It's as if like I'm not making this up. Okay, so you look at the pages of things like Combustion and Flame, or Proceedings of the Combustion Institute, or Combustion Science and Technology, Combustion Theory and Modeling, any of these things, you will find people who are actually doing these kinds of things. So it is not it's not just to boast that we have a lot set. It is something like a burden that we have to go through. Right. Then we have to think about, is it required for you to actually keep cranking these numbers all the time for each and every term in each of these equations, because you have like a large number of equations and so on. There are many ways by which you can handle these things. Like for example, if you now are thinking about a typical equation, keep in mind we have a convective term, we have a diffusion term, and a reaction term, right? So these three terms have their own typical timescales. That means you don't have to necessarily evaluate each of these terms in each and every equation all the time. That means you are just cranking up numbers, right? The idea is the reaction time scales are typically very, very small. Things are happening pretty fast. You are looking at fast chemical reactions in the reaction zone, right? So when you now have fast reactions that are happening, the time scales for these reactions is so short that the flow is hardly moving when you are now trying to evolve how the composition is changing because of the chemical reactions. So for all you care, you could actually freeze the flow, okay, and advance it over a large time step, and during this time you can now do your chemical calculations alone. You don't have to worry about the flow field, it's like frozen, right? So that means you go back to an expression that looks like this and then say this is dCi over dt, like an ODE, alright, at a particular place, and then you now are given a concentration set of for all the species at that particular point. If I now take a small time step here, how will I advance to the next small time little later to change the concentrations based on just a time integration of this set of equations, okay, given that the temperature is whatever it is right there. alright, and then keep doing this for quite some time until the composition has significantly changed, and then start moving this around, mixing it with other places and convecting it and so on. Then you now bring in the other parts of your the other terms of your equations. So this is like a multi-time scale approach that allows you to what should I say, reduce the amount of calculation that is required, you see. So you can now look at this like a separate package that will keep on cranking before you actually crank the fluid mechanics, right. So that means you don't have to worry about taking small time scales to resolve this and the fluid mechanics simultaneously. The fluid is not going to take these species too far from where they are as they are changing because of chemical reactions, so you can freeze the flow during this time. So you can take these kinds of approaches to simplify your life, but life is certainly complicated if you now look at the full combustion problem. What we would do from now on is we now have actually looked at the full combustion problem. We have posed the combustion problem, okay, for any situation. This set of equations is now valid for any situation of combustion problems. What we will try to do is it possible for us to simplify this under certain conditions. So we have now reached like a summit, and then we will keep going downhill to make it easier for our lives, and then we will now start looking at specific problems, like let's say a premix flame or a diffusion flame and so on, within a simplified framework that is handleable from a theoretical point of view, rather than having to rush to a computer every time to do anything, right. So this is the way the rest of the course is going to go from here. This is like the starting point. From here we will now go simplifying things.